Hello, welcome back to your Module 2. Still on your analysis of your statically indeterminate structures using consistent deformation method. Okay, so in your Unit 1, we discussed on how to analyze statically indeterminate beams. And in this Unit 2, we will now be analyzing statically indeterminate frames. Okay, using still your consistent deformation method. So in this unit, okay, so here is your unit learning outcome. First is, of course, in your method of your, or I mean in your analysis of indeterminate beams, we use there your conjugate beam and then moment area method. But in here, we will be using your virtual work method. Okay, so we will try to recall if ever you discuss this one, but if not, then I will be introducing you this virtual work method of determining deformations, rotation, and deflections of your frames. Okay, and actually your virtual work method is also used in beams and also in your trusses. Okay, so this is what we will be using if we will proceed to your trusses. So we need to recall what is virtual work method. Okay, and then of course we will be analyzing indeterminate frames using your CDM, that is your consistent deformation method. And then of course you need to know again how to formulate compatibility equations based on the type of supports given on the frames or in the structure. So okay, let's start with your virtual work method. We will try to recall this one. So how are we going to get deformations of structures using this virtual work method? If I will discuss the derivation of this, that will be a little bit tedious, so it will take much of our time. So if you want to know how this is derived, okay, this is actually just derived from your, if you will recall your dynamics of rigid bodies and then of course deformable bodies, your work energy method of determining your strength, and at the same time of course the relating kinematics with kinetics. Okay, so that is where this virtual work method is derived. Okay, so you can go to books and then take a look at how this is derived using your work energy. Okay, so in your virtual work method for the deformation of beams and frames, okay, so this is true for beams and frames, because if we will go to trusses, this will be different, and we will try to recall that one if we will go on analysis of indeterminate trusses. So this is for beams and frames. So again, since we are done with your beams, you can go back and apply this one later on. You can use this as your checking. So deformation of beams and frames, in delta there is again your deflection, and using virtual work method, that is summation of the integral, okay, from with the limit a to b of your big letter M times small letter m all over ei times dx. So we are using here now moment equations. So if you will try to recall other methods like double integration, you are using there the moment equation. So if you say moment equation, that is the moment, the equation that is representing the moment on any point on the beam, okay, with a given loadings, type of loadings. So this is of course a little bit challenging if you still do not know how to make use or to create your own beam equation. But if you already tried that one, or if you already know your double integration method, then this will be a little bit easier, okay, using your virtual work method. So again, what is that m and small m, the big letter M and the small m? These are your moment equations, but what is the difference of that big and the small? Your big is the moment equation of any segment, okay? By the way, if we say segment, we are trying to divide the beams or the frames into segment or into lengths, according to the type of loadings. Okay, so there are some length on let's say there will be a certain length on the frame or beam that the equation of the moment will be the same, so we will consider that as a single segment. But once you will let's say proceed to the other length or other points on this structure or beam or frames, you will end up with additional loading, so the moment equation on those segment or span will be different from the previous one. So we are trying to divide your frame or beam into segments, and each segment should have the same moment equation. Okay, so that's why we have here summation, because if we will consider, since if we want to get the deflection or rotation, we need to consider the entire beam or entire frame. So we are using here the summation, because again you might end up with more than one segment. Okay, so again the M there is the big M is the moment equation at a segment due to the actual load. So if we are talking about, let's say, let's take this beam as an example. Okay, so as you can see, there are UDL, there is a UDL, and there is a concentrated loading here. So there will be a lot of types of loading that could be applied on your frames or beams. And if we will try to take all of that, all of the external loading, okay, or the actual loading, and we will try to find out the moment equation in each of the segment, then that is the moment equation due to the actual load. But later on, we will be applying what we call as the virtual load, or actually just like in your um, just like using our conjugate beam. Okay, applying here your unit load, or in this method we call that one the virtual load. Okay, applying that one on the point that we are trying to investigate. So let's say you want to investigate, okay, moment at the segment due to the virtual unit load. Okay, so for example, you want to get here the deflection at point E. Let's say you have here this A, B, C, but you want to get that point E, the deflection at that point E. Then all you need to do is apply a unit force. If you are using here, or if you are after a deflection, what we are going to apply, a unit load that we are going to apply is a unit force. So if your units here for the forces are kilonewtons, then that will be 1 kilonewton, but if that is kips, that will be 1 kip. Okay? So later on we will proceed with your rotation. That will actually be the difference only. That is just the only difference, the unit load or the virtual load. And again, we will end up here with the big M, that is the equation due to the actual load, and then the equation due to the virtual load. Multiply that one together, that will be a function of x. Okay. By the way, we are talking about here equations in terms of distance, and we will put that one as x, or if you want other variables, you can use other. But let's say I will consider x, so I will of course consider a point of reference. So if I were you, I'd rather consider the very first point. So let's say that is where I will reckon my x. So for example, in this case, what are the segments, or how many segments do we have? If you will try to consider this point A to point B, that is the same loading. Okay, in the case if I will cut at any point in this AB, segment AB, you will have the same equation, because what are the moments that will apply on the segment is later on you will have here the reaction, the moment of reaction, and the moment of the UDL. So if I will cut here the moment of the UDL and reaction, if I will cut here moment of UDL and reaction, so AB is considered as one segment. Now we will go just after B, after point B. You will not have there a UDL already. Okay, you have your UDL here, but that is now terminated at point B. But once you will go on within the segment B to C, you do not have that UDL the straight, or that is not a full span of UDL. So it means that your equation will be changing, since that UDL is terminated at B. So you will be having another equation here at segment BC. So still you will reckon your distance x to any point from this original assumption a while ago, which is point A. And then once we will proceed here, just after C, there will be additional loading. So again, there will be another changes, or there will be a changes in your moment equation. So this will be considered another segment. That's why we have here limit A to B. So in this first segment, you will have your equation here, and your limit is from 0, since of course we reckoned our distance from point A. So from 0, if that is meter, so 0 meter to whatever the length up to point B. So that is your limit here, A to B. And then integrating your segment B to C, your of course either or your lower limit is the distance of B, and then your upper limit is to C, the distance of A to C. So again, this is just integration, guys. This is the definite integration. And then of course limit is in this third segment is from C to D. So whatever the distance of C from A and D from A. So as you can see, those are where you will be getting the equations of your big M. However, in your small m, actually the number of segments here will just be 2, since actually, or 3, it depends actually on where you are trying to get, or even one only equation. It depends on where you are trying to get the deflection. So let's say again, since you are after point E, the deflection at point E, then apply a load, unit force or a unit load at point E. Okay, just like in our conjugate beam method, using conjugate beam method on the analysis of beams, if you predicted that that will deflect downwards, then better assume a downward force, okay, or assume a downward force, so that you will end up positive if that is the correct assumption. But if that is the other way, that is negative, okay, so it means that is the other way of deflection. So again in here, so as you can see, there are only two segments, so this segment and then another segment from E to D and A to E. So as you can see, if we will try to get, we will of course consider your first segment A to B for your big letter M, but the question there, what will be my small m? So as you can see, if I will try to align here what is the point B, that is your point B. So it is one segment in your actual loading, but in your virtual loading, I need to cut that one into two segments. Therefore, your AB in your big M will be divided into two segments again. So again, let's now consider this as one segment, A to E, E to B, B to C, C to D. So a total of 4 segments. So your big M is in your first segment is this one, and then the small m will be get from this. And the big M in your actual loading is here, and you will be getting here, whatever the equation of your virtual loading here. And that will be all throughout. The equation of your virtual loading is the same from your EB, BC to CD. So your 3 remaining segments has the same small m. So the only different here is the small m of your first segment, which is from A to E. So again, using virtual work method, you need to know how to divide your segments. Okay, you need to know how to divide your segments, because if you will now let's say in here you forgot that E there is within your span or segment AB, and you made your small m constant from segment A to B, then that will already be wrong. Okay, even if you will now continue and be solving the whatever is being asked. So that is your deflection using virtual work method. How about your rotation? Okay, so actually the same. The only difference here with the deflection and rotation is that the small m will be actually the equation or moment equation applying a virtual load which is a couple or a moment, a unit moment or a unit couple at the point we are considering. So a while ago, still, let's say we will still consider point E. So a while ago, we are after a deflection or a distance, deflection distance. So that is the unit load or the virtual load that we will be applying is a force. Okay. In your rotation, what we will be applying there is not a force, rather it is now a couple or it is now a unit moment. Okay. So the same, we will apply that one at point E. So what will change here, actually, if you started from your deflection, what will just change here is your equation of small m. Since what we will be changing here is just the loading of the virtual load. From force, we will just be changing that one to couple. So again, if that is what you need, if what you need is the rotation, okay, by the way, again, what is rotation? That is the angle from the beam, original orientation of the beam to the tangent line to the point on the elastic curve, okay, of the beam that we are considering. So E, that will be deflected to that point and draw a tangent line. Then again, the angle from your original orientation is your rotation or the slope. The others call this one as the slope. So that is virtual work method. Okay, dx, of course, we need that one since we are integrating differential equation. And actually, again, EI is constant. If EI is constant, that is just a number, so you can bring that outside the integration so that it will not interfere. You do not need to be writing that one again and again. But if that is difference, then again, just like what I've discussed before, you need to consider the difference of E and I. Rather, you will substitute or you will use a common I in terms of the other I. So let's try to have an example here. Okay, let's try to have one example in your frames. So if you'll try to look at your frame, okay, but without even solving, you can actually decide that this is a second degree indeterminacy. Okay, why? Because this is a fixed, so there are three supports, and this is pin, so there are two supports, so that is a total of 5 restraints, and we only have three equations since there are no equation of condition. So subtracting 3 from 5 is 2, so that is a second degree. But if you can see, you might be, you do not need actually to check here. But if you want, you can check the internal indeterminacy. But actually, we do not need that one. Since once we get the reactions here, this is simple frame, so you can actually just cut that one and then bring out the forces or solve the internal forces. On your, you can draw your shear in moment diagram. Actually, do not interchange. Please do not interchange your truss and frame. If you say truss and frame, there is a moment on the member itself, while on truss, that is just a tension or compression members, okay, in your trusses. So again, just like the procedure that I've discussed on before we started with your unit 1, you will be following there the 4 procedures. You need draw, of course, your release the redundant, so choose redundant here. So for me, okay, there are a lot of ways again, but you need to consider the stability. So if you want, you can actually remove the entire pin so that you will release 2 redundants already, and you have here 3 remaining restraints, which can be solved later on using your statics. But okay, it's up to you if you want to. But if you will be doing that, you need to satisfy the condition that the original deflection at D horizontally is 0 and vertically is 0. So that is for you will be getting your 2 equations of compatibility. But for in my case, so that we will be ending up with a rotation and deflection, I will be removing my, or I will be releasing the moment here. And let's say I will also be releasing one of the restraints of force restraints here, which is the horizontal. So that is what I choose. Okay, so if I will release the moment and the horizontal, then this will make my support a ruler. So if that is now a ruler, only one reaction, which is vertical, and in the pin there are 2, so this is a 3 remaining reaction or restraint, so that is now determinate structure. Since again I released your AH and MA, so this will now be an unknown force. And again, what will I need to satisfy here? Since that is now a moment, I release a moment, so I need to satisfy the rotation. Since originally that is a fix, so there should be no rotation. So the rotation at point A is 0. So I need to satisfy that one, or that is where I will be getting my first equation or second equation in compatibility. And then the second there is, since that is originally fixed, again there is no translation horizontally. So okay, you need to be careful here now on frames. It's okay with beams because most of the time, if your beams is the same elevation, you do not need to worry about deflection horizontally and vertically at the same time, okay, unless there is a settlement in your support. But on frames, especially in frames, if you're releasing when the supports of frames are not the same elevation, then you need to be careful actually in releasing the vertical and horizontal components. You can do that here, releasing your point D, horizontal, vertical, but you need to consider your horizontal deflection and vertical deflection separately. So again, okay, so this is my determinate structure. So let's assume this is the deflection due to the loading. Okay, so that is the deflection due to the loading. Still, this will not move, even if that I made that one as ruler, because of course originally that is fixed. So that will not move. So the deflection, it will not move. That is being restrained by your AH. Okay, it is now restrained by our AH. So again, I do not know originally the direction of this redundant, so all I need to do is assume. And then if later on I will solve and you will end up with a negative, that means the assumed direction is opposite. Okay, so let's proceed. I need to break this down. Okay, so the actual loading again, or the external loading, And then of course, since I have two redundants, I need to apply the two redundants separately. So actual loading, what this could be my deflection. Okay, since again in my actual loading, forgetting about the redundant, let's say there is no restraint horizontally, so that might deflect that way, or yes, deflect that way. So we have there a horizontal deflection. Okay, horizontal deflection. So let me call that one as delta AL. That is again deflection at A due to the actual loading. And of course that will rotate since that is not a fix. So there will be rotation here. So from the original vertical orientation of that AB. So let's say that is the rotation at A due to the actual loading. And then of course we will apply your first redundant. Let's say that is your horizontal AH. So if I will apply that redundant, okay, that will now serve as a load. This might deflect that way. Okay, by the way, what are these 90 degrees here? That is a frame. Okay, that is a frame. So there will be no adjustment or there will be no deformation on the connection because that is a frame. It is formed to be a fixed connection. Not in unlike in the truss that the connection will actually adjust since that is a pin. But in a frame that will always be the same orientation. So if that is originally 90 degrees, then that will always be 90 degrees. Okay, so again, this is the redundant AH, so that might be the deflection. So maybe that will be the rotation and deflection. So again, let me just discuss the subscript that I use. Again, as I've said, since there will be a horizontal and vertical deflection, I need to differentiate them. So to differentiate the vertical and horizontal displacement or deflection, I will write there a deflection at A, H. That AH stands for deflection at point A horizontally. So later on, if that will be AV, that means deflection at A vertically. Okay, and what is that other AH there? Due to our redundant, which is a or horizontal force at A. So again, that is your AH. Again, that is the horizontal deflection at point A due to the redundant horizontal at A. Okay. So in your rotation, there is no other rotation, only a rotation which is clockwise and counterclockwise, and actually you can represent that one as 1. So I can just say that is theta sub A. It means that is the rotation at A, and that again AH is due to the redundant at AH or redundant AH. Then we have one more redundant, which is the MA. I will apply that one at A. So again, what that might be the deformation again of our frame, and you will have here a horizontal, again horizontal deflection. So that's why I am using here this subscript. Your subscript is a little bit complicated, but actually that will serve its purpose, because later on if you do not have that AH there and that AM there, you will not differentiate the effect of these different redundants. Okay, so to differentiate them again, that is the same still horizontal displacement at A. So again, that is your AH. It means horizontal displacement at A. And your AM there is due to the moment at A. So that M there is the moment. A while ago that H there is the horizontal force at A. Because later on you might be having another redundant here and so on and so forth. So again, but if you can figure out another way to make use of your subscript or to define your subscript, it's up to you. So again, your rotation here is again rotation at A due to our moment at A. So I need to go back to the original situation wherein that is fixed. So this is just the primary frame or primary structure, the resulting determinate structure. But the actual is that is fixed. So even if I will now summate all that horizontal deflections there, that should be 0 because that is fixed originally. So that is where I will be getting my first compatibility equation here. But however, again, that delta AH and delta AH we cannot get that one directly, since in the first place you do not know this AH and MA. These are the redundants. So what we are going to do is apply a unit load or a unit force in in what we call this one, in the placement of AH, and then a unit moment or a unit couple in the placement of MA. Then of course, just like in your unit 1, this will be the ending equation for the for satisfying the summation of deflection. Now summation of rotation, satisfying that one is the same, and then you will end up here again, and that should be 0. So you have now your two equations. Your two equations of compatibility. Okay, now all we need to do is find this delta AL, theta AL, and these coefficients here for us to use the two equations to solve for the AH and MA. Okay, so let's start with your primary, or I mean with your external loading. Okay, let's start with the external loading. So again, just like before, apply your external loading, forget about the redundant, and solve for the reaction. And now we are on virtual work. So what we need is to integrate, or first is to find out the moment equations due to the actual loading in the virtual loading before we'll get that these deflections and rotations. Unlike in your conjugate beam and moment area method, that you need to draw your shear and moment diagram of the actual member, and then of course get your M over EI, and that is where we will be getting your delta and theta. But since this is virtual work method, that is applying your equations and integration. Okay, so we do not need to be drawing here the shear and moment diagram of each of the member. So in here, all I need to do is, of course, since in each of the member, just like in a beam, okay, frame is actually a combination of beams which is oriented vertically, horizontally, or even inclined. Okay, so that's a frame. Unlike in beams, that is just of course a horizontal, if that is a horizontal beam. So in here, the same, consider segments. So what are the segments here? I need to consider AB, BC, and CD as one segment. However, if there will be a variation on the loading along this in each of the member, I need to break it down in another segments. However, it seems like AB, there is the type of loading here is uniform, so I will consider that as one segment. And then in your BC, again, there is no change in the type of loading and reaction, so another segment. And then your CD is uniform also, so another segment. So we only have here 3 segments due to the external loading. So again, solve your reaction. Okay, it's up to you. That is the summation moment, and then vertical and horizontal. Okay, so you will end up there with your reactions, but I need to figure out, or I need to break down the segments and then get the equations of your moment equations. So if I will cut that AB, you will expose the reactions or the internal reactions of this at this point just after your support. Of course, you will have there this 25, which is coming from your reaction or your support. 25, which is compression or going up. So again, going up, and the right is positive, or clockwise moment is positive. So that is my sign convention. And then there is no horizontal here, so of course your horizontal there is 0. So summating horizontal, your horizontal on the other end is 0 also. Summating vertical, that is going down since that is going up. So this is now in equilibrium. If I will try to cut at any point there, since that is considered one segment, so the moment equation in any point here in your member AB is the same. So let's say I will cut at this point. Let's say that is distance x. My origin there is at point A. So okay, in your virtual work method, it is suggested that you will write down your equations or your result or your solution in tabulation form. Since, especially if you will end up with a lot of segments, okay, better write it down in tabulation form, so that if you will try to review or you made an error, then you can review it one by one. Because if you will write it in terms of equation directly, you might end up there with an error, and it is hard for you to figure out later on. Okay, and we will be having here limits and origins, so you need to tabulate this one since these are a lot of data. Okay, so where I reckon this origin is where I reckon the x on your segment. So I reckon that one at A. So that is my origin. So that is how I will write my member also. AB, because I reckon from A, or my origin is A. Write that as BA if your origin is point B. Okay, so again, uh, I will take it as clockwise. So if as I go on clockwise, I will be considering the left side always. So actually clockwise. So the first part I will considering the first part going clockwise in my frame. But if you want, especially if you have a lesser force and you want a simpler equation, go to the other part of the free body diagram. You need to change your assumption of direction. Okay, just like in your beams. So in here, that is, I will cut that one, and what will be the moment there is actually, there is no moment because that is a force going to the point, or that is a concurrent force. So there is no moment of those. I am considering this part. Okay, if I will cut that one. And that is 0, so there is no moment. Okay, there is no moment horizontally. There is no moment due to that horizontal force. So actually your moment equation there is 0. So that means actually that in this member AB there is no moment in this scenario. Okay, in this scenario of the frame there is no moment. But if you will go on the actual scenario, since that is fixed, there will be a moment. Again, this is only in this scenario since that is ruler and there is no loading in your member itself. So actually there is no moment here. So my moment equation there, M, I will be writing those at your big M because that is your actual loading or external loading. So my moment equation at AB is 0. Again, your limit there is from 0 to 15 since that is the length of my AB. Later on, we will fill this up in your virtual loadings or in your redundants. How about BC? So transfer your reactions. The 25 will go from downwards, it will go up, it will be transferred there going up, and then 0, so there will be no transfer from the AB to BC. However, we know that there is a force applied in this point, so that will be now added. Even if that is 0, that will now be added, which is going to the right, so that will now be going to the right. Okay, so that is just of course your member forces, recalling your theory 1. So we have now here from 0, we have now the 10 again because of that force here. So that is now 10 going to the right. And then of course your actual loading here, which is a UDL 2 kips per feet. And then of course getting the reactions on the other end, summating horizontal, you will have that going to the left 10. Okay, sorry. Yes, it's okay. This is correct. Summating vertical, since this is load, you can combine that one and then subtract 25, you will end up with 35. 2 times 30, since the length of that of 30, so that is 60, minus 25, so still going up, which is 35. And then if I will to take, in here, if I will to take moment, there is no moment. Okay, so there is no moment reaction there. So there is no moment that I will be transferring here. But if I will take a moment here, the effect of the forces will actually not cancel out. They will end up there with a resulting moment which is counterclockwise due to this 2 feet is bigger than the 25. Okay, so that will be counteract by a reaction at this end which is 150. If you will try to evaluate the moment at that point from this 2 feet and the 25, you will end up here with 150. Okay. So these are the forces that we will be transferring later on the next. But first, let's try to figure out the moment equation here. So again, that is one segment. So any point here has the same equation. So I will just cut there, that is a distance x from my point origin B. So I will write it as member BC. My origin is point B. The limit there is 0 to 30 since that is the length. Okay, so if I will cut, what are the forces? I will still be considering the first part. Okay, so that I will follow my sign convention. So clockwise is positive, so that is at this point, moment there is 25x, positive 25x clockwise. And the moment, there is another moment due to your 2 feet. But we do not know what is that force, so actually, okay, do not be confused how we ended up here. That is just the resultant of that 2 feet that we considered within a distance x is 2 times the distance x, the resultant of that. And what is the so that is 2x. But what is the moment arm to that point here is x over 2. Okay, half of that x is the moment arm since that is applying at the middle. So 2x times x over 2, you will end up here with x squared all over 2. The 2 on top and the 2 below will cancel out, so that will end up with negative x squared. So again, that is how we ended up here with negative x squared. So that is your moment equation. And there's no other force that will create a moment at that point x. So that is our moment equation at BC. Proceed to your CD. So again, I will take it as CD so that my origin is C. So I am just going clockwise. So I will always consider the first part as my diagram. Okay. So actually, if you will try to flip that, that will become your left side. Flip that, that will become your left side. So just like on beams. But transfer now your reactions. This is going up, this will go down as 35, and this is the clockwise 150 that will go counterclockwise 150, going to the left 10, that will now go to the right 10. And then of course you need to satisfy the reactions at the end, another end, going down, so that is going up, that is to the right, that is to the left. But if I will summate moment here, if I will summate moment at this end, this 150 is actually counteracted by that 10 times the length, which is 10 times 15 is also 150. So the moment at this end is 0. Why? Actually, you can verify that one, since there should be no moment at this support, since that is a pin. Okay? So there is no moment reaction. Therefore, there should be no moment here. So now, drawing the equations of the moment due to the actual loading at this member CD, my origin is C, so I wrote it at CD. And then the limit is from 0 to 15, since that is the length. And again, what is the moment at any point here? Say that is a distance x again from point C. Clockwise, 10 times x, so 10x. And then minus 150, there is no moment arm, since that is a moment. So this is my moment equations on AB, BC, and CD. Now let's proceed in getting that moment equation of the virtual load redundant AH, and then later on moment equation of the redundant load moment at A. So we will proceed. So now let's start with your moment equation due to the redundant AH, but again we do not know that, so we will consider a unit load. Okay. So one keep there. So getting the reactions, submitting horizontal or getting the moments, actually there is no vertical reaction, only a horizontal. So that is one keep, this is also one keep. So that is our only reaction. So again, cut your members. This will be one segment, one segment, one segment again, since there are no variation of loadings in A, B, B, C, and C, D. So considering your AB, so the same, my origin I will follow. Of course, what you followed here as your origin and then flow of your analysis should be the same on the redundance. Okay, that should be the same with this redundance. So again, I will always consider the first part as my diagram. So I will cut what is the moment. Okay, okay. By the way, let's figure out how did these reactions end up. Let's horizontal to the right one. Okay, summating it, there is no vertical, so of course I do not need to write that, or you can write that as 0. Summating horizontal, you will have here on top counteracting that to be going to the left one. Getting the moment here will actually be counterclockwise, so it will be counteracted by clockwise, which is 1 times the length, which is 15. So the moment here at this end is 15 counterclockwise. And transfer this one, since there are no external load that will affect that one. This will be originally clockwise, that will go counterclockwise. To the left, that will now to the right. And then transfer that on the other side, since there are no external loading here, that will just be equal with each other but opposite direction. So that is to the left, that is now clockwise. Again, there is no external loading at that point, so that will just be transferred. So from clockwise, it will go counter. From left, it will go to the right, and then of course, there is no external loading. So again, summating. But if I will take a moment here, that 15 clockwise is counterclockwise is counteracted by 1 times the distance, which is 15, which is clockwise. So that the moment here is 0, since again that is a pin. So that is how we ended up with these forces here. Now get the moment equation. So I will write that at m sub ah, small m sub ah, okay, to differentiate that later on due to your moment. Okay, at this AB, I will cut there. What is the moment? That is only due to your 1 keep, which is clockwise, counterclockwise, which is negative 1 times x, or that is simply negative x. Cut in here, any point here is a distance x at that origin. So what are the moments? Actually, that is the only your 15 only, which is counterclockwise. Therefore, that is negative 15. There is no moment of that one since that is concurrent, or that will be going to the point we are considering. And then on your third is that I will cut there any point. What are the moments? Actually, clockwise due to the 1 times x, so positive x. And then a counterclockwise moment, which is already a moment, so that is 15, minus 15. Proceed using to the other redundant 1 unit couple or 1 unit moment. This will be your resulting reactions here. There is no horizontal. And then breaking it again, what are the forces? So counterclockwise, which is 1 cube feet, going up 1 over 30. So that will be transferred 1 over 30 going down, and then that will just become counterclockwise. I mean clockwise. Again, there are no external loading, so you will expect that this will not be altered. Okay, so this will be transferred as counterclockwise. That will be transferred as going up. That will transfer as going down. But if I will take a moment here, okay, at this point. Okay, by the way, why is it that in here there are moments, but in there are no moments? Because again, if I will to take moment at this point, there will be an effect of this, which is exactly the same but opposite direction. But if I will consider at this point, that effect of that moment there is actually counteracted by the effect of our 1 over 30 times the distance, which is, of course, 30. So that will be 1 also. So there is no moment here, only the vertical, which will now be converted into going down. There is no horizontal, so there is no horizontal. So that is the only force that will be transferring here, so that is going up, so that will now be going down here. There is no moment, there is no moment. And which is true because that should be equal to our reaction here. And there is no moment since that is a P. So getting the moment equation here is that, okay, under I will write that under your column M sub AM. It means that is the moment equation of virtual load due to the redundant at A, which is a moment. So AM. So at this point, I will cut what is the moment that is actually due to your couple 1M with 1 moment, which is counterclockwise 1 negative 1. I will cut there. What are the moments? These are due to your moment and the force. So clockwise 1 over 30, so that is 30 over x over 30, and then counterclockwise moment, which is 1, so that is minus 1. And then cutting this one, there are no force that will create a moment in this member, so in this case, this is momentless, or this will not be subjected to a bending moment, okay, which is only subjected to a tensile if I will apply that load here. So there is no moment there, so that is 0. Okay, so we completed now your big letter M, small letter m, and then small letter m. Okay, so let's go and solve now your coefficients of our equation. I will just copy now this table, so that's the table here. So from this one, from the deflections, the deflection equation that we established a while ago, your deflection AL is due to the actual load, isn't it? Due to the actual load. So again, if you'll try to go back there in my discussion, deflection is the moment equation due to the actual load and the due to the multiplied to the virtual load moment. However, we have here two. We have there two moment equation of virtual loading. So I will explain which one we are going to use. Since there are two equations, then that is where we will be using one of these, but this should not interchange. Okay, since we are talking about here a deflection, and what did I say? If that is a deflection, you are after, you need to apply a force. So I need to use the virtual moment equation of the force. This is your force, isn't it? And we are talking here of the deflection horizontally. But if we will go later on the unsatisfying the equation or completing the equation of rotation, then we will be using the virtual loading of your couple. Since again, if you're after a rotation, apply a virtual load which is a couple. So that will be your small m later on. Okay, so now this is big M and then small m AH, since we are talking about horizontal displacement here. So integrating that one. So all you need to do is multiply your moments equation and then integrate that one given the limits. So all we need to do is satisfy. But since again I've given there on the problem that your EI is constant, Okay, EI is constant, so you can factor out your EI. Okay, so now let's start with your segment AB or member AB. But again, later on, if you have the variation of loading at AB, you need to break that down into segments again. So AB, since that is one segment, the first segment, from 0 to 15. However, there is no moment equation of that, because even if there is in your virtual loading, that is 0 in your actual loading. So even if there is your MAH, if there is no big M, then this will be useless. So I will not be having integration at your member AB. Okay. Now BC, there are values, so I can now have equation there. I will combine that one, so that will give us this. Okay, so that is just actually, okay, combined, multiply that one, you will end up here. And then of course your limit is from 0 to 30, so integrating that one. And then your CD, now your moment M, big M and small MAH will be multiplied, so that will give us this. And then your limit is 0 to 15. Okay, so these are the only moment equations that we will be integrating, since again your AB ended up 0. So integrating that one and multiplying your E1 over EI, you will end up with a negative 22500 over EI. Then, okay, that is just your delta AL. That is the deflection due to the actual loading at A. Now, you need to find these small deflections due to the, this one is due to the horizontal redundant, and this is due to the moment redundant at A. So we will not be using now your big M in getting these values, since again there is no effect of your actual loading. So what I will just be considering are your small moments. So do not be confused here, since we are talking here of the horizontal deflection due to the horizontal redundant. So that big M will just become itself, which is small MAH. Since again we are considering the loading as the redundant, and we are considering the virtual load as itself. Okay, if you will try to go here. In your deflections, we considered your big M as your external loading. And then whatever the virtual loading that we will be considering, it depends if that is a deflection or rotation. But since we are getting the moment M, small m only, then we will only focus on the virtual loading. So if you want to get the deflection at this point due to this redundant, then that is just raising this one to 2, or multiplying this M to itself, so that we will satisfy that M times M here. Moment equation times moment equation. So since we are getting that horizontal displacement at A due to that horizontal redundant at A, all you need to do is square your MAH. Okay. So I will square that MAH. So I will just focus here, square that one, that is positive x squared, integrate from 0 to 15. Square that one is positive 2 to 5, integrate from 0 to 30. Square of this is this equation from 0 to 15. You will end up with 9,000 over EI. Okay. Again, do not be confused. I will proceed here with the next, which is FAHAM. So again, that AH stands for horizontal displacement or deflection at A. So I will be considering there my virtual load, okay, my unit load as the horizontal, which is this equation. And then that is, that is due to the moment. So now, due to the moment, small horizontal displacement due to the moment. So all I need to do is multiply your MAH and MAM. So multiply this, positive x, integral 0 to 15, multiply this one, this is your resulting equation, 0 to 30, multiply that one is actually 0, so there is no need to write that one. Integrating that one is positive 675 over 2 EI. Now, substituting that one to our equation here, you will end up with equation 1. Okay? And now, let's satisfy the equation of rotation. So again, we are talking here of rotation. So, in your actual rotation, due to the actual loading at point A is the big M times now we are talking here of rotation, so we will be using the equation of the virtual loading due to the moment. So multiply that one. So again, useless. Your first AB is useless since that is 0. So I do not need to be having that one. But in here, that is, this is multiplied to that, you will have this complicated, integrated from 0 to 30, and multiplying that CD is actually useless since that is 0. So the only integration is your BC. Big M times MAM. So that will be giving us, multiplying 1 over EI, negative 1500 over EI. And then if AAH. So what is that if AAH again? Again, since there is no subscript of that A, it means that is rotation. Rotation at A due to the horizontal redundant. So rotation, we are talking here of the loading to be rotation. So MAM times due to the horizontal, so due to the MAH. So actually, if I will multiply that one, isn't it? We did this one a while ago, which is this one, MAH, MAM. However, the only difference is that their what do you call this one? Their arrangement. MAH goes first before MM a while ago, but if you are just multiplying the equation, that doesn't matter. Okay, that doesn't matter. So actually, you will still end up with the same here a while ago, which is 675 over 2 EI. 675 over 2 EI. Okay, multiplying these two. And then later on, this is now FAAM. So that A again is rotation due to your moment. So rotation due to the moment. A while ago, that is rotation due to the horizontal. So rotation times horizontal. Now this is rotation due to itself. So square this one. Square that one. So if I will square this is positive 1 dx. 0 to 15. Square this one. This will give this one from 0 to 30. Square 0. So that is useless. Well, we will end up here with 25 over EI. Substituting these values to your equation here on top, you will end up with the equation 2. Now, solving simultaneously, you will end up with AH to be 40 over 79. That is the whole value or the exact value, which is equivalent to 0.51 kips. And then your moment at A, again, these are what we solved since these are the redundants that we assumed, is equal to 4200 over 79. That is the exact value, or in decimal, that is approximately 53.16 kips feet. And then the rest, if I will now apply this AH and MA, the redundants that I already know, to my original structure, then the rest three reactions will now be solved by statics. Okay, so summation of forces horizontally, what are the forces? Is your AH, your 10 kips, which is, I assume, going to the right is positive, so these are positive, minus this unknown DH. So you will end up there with DH to be 10.51. Okay, sorry, let me just change that one to the whole number. Let me just change that one to our whole number. So that we will have their exact values. Here's my laptop, calcu. So you have their AH plus 10, so 10 plus our AH is 40 over 79. We will end up there with 830.79. 830 over 79. So that we will have our exact values. Okay. So that we will have our exact values. So again, your DH is now 830 over 79, or that is 10.51, approximately 10.51. Now, submitting moment at A so that we will get that vertical reaction at DB. You will end up with clockwise, which is 10 times the moment arm, which is 15. And then, of course, this UDL here, I need to convert that one into a concentrated load. 2 times 30 times what is the moment arm? The middle of 30 is 15. So clockwise, positive. And then your moment, which is a negative, since that is counterclockwise, but I will be using the whole number, 4200 over 79, negative. And then the moment of your unknown dB, which is counterclockwise, negative. Moment arm is 30 times that unknown dB. So solving that dB is 2625 over 79, or approximately 33.23 kips. Now, the only unknown is your AB. So instead of getting the moment here, you can do that, but I'd rather use of the vertical, okay, summation vertical, which is going up positive. AB is positive, DB is positive, and then the only vertical here is the force of the UDL. 2 times 30 going down, so negative. So given your AB to be, where's that? AB. I mean DB, since that is what we solved, 2625 over 79, substitute that there, you will end up with AB 2115 over 79, or approximately 26.77. Okay, so that is how we ended up with your unknowns of your frames, reaction in your frames. So again, if you need now your shear and moment diagram, again, since you are used with drawing shear and moment, all you need to do is go back to just like what we did here, uh, expose the external, I mean the internal forces, and these are what you are going to use to draw the shear and moment diagram of AB. Okay, so using of course whatever we solve here. Whatever reactions, transfer that one to your member AB and then solve the corresponding reaction at the other end. Draw the shear and moment diagram of this separately. And then transfer the loading and then get the reaction there, shear and moment diagram of your BC. And then the same thing with your CD. Okay, so that is frames. Shear and moment diagram is of course be drawn from your forces. Okay. So these are the important concepts, but as this is what I've discussed before in your unit 1, so you need again to consider stability of the system if you are choosing your redundance, and of course you need of course to be assuming preliminary directions in your forces and couples. If you do not know that one in the first place, then if that is negative, that means your assumption is just the other way. So again, that is for your frames. So if you have any question, please comment that one below the video so that we will discuss on the next meeting. So thank you very much for listening.